This recording is going to have to be in two parts because the power went off. So I'll save it at part 1 and part 2 if anybody watches them. Okay, so the left Riemann sum, most of the work is already done. We had our partitions, and we have now the left endpoints for each partition, or subinterval rather, to determine the approximate area using the left Riemann sum. So we'll have the area using the left Riemann sum is approximately, and this time we'll just put our delta x out here, and then multiply that by the sine of all of these red values. So what we have to do is just shift that pi over 12, pi over 6, pi over 4, pi over 3. Same function, same partitions, same subintervals, different values. So we type all of that out into our calculators. Should come out to be 0.863. You got that? And just for reference, again, we have our image here. We see this time, though, the left endpoints that we're using, the left endpoint. So the height of the first rectangle is 0, but then we're using all of these points here for the height of subsequent rectangles. We see that's an under approximation of the area. Does that make sense? Does anyone have any questions on that? Then the midpoint Riemann sum, we're not actually going to work through all of that. But again, it's based on our delta x and our subintervals. And we're just going to take the midpoint of each one of these subintervals. So halfway between 0 and pi over 12 is pi over 24. Halfway between pi over 12 and pi over 6 is pi over 8, and so forth. Whatever all of these midpoints are, those are the values we're plugging into the sine function to evaluate the midpoint Riemann sum.
Generally more accurate?
Yeah. The midpoint is more accurate because it doesn't give us an under or over approximation. It's kind of average of the under and over.
If we're having to take the left and right Riemann sums and we take an average of those two values, is it equivalent to the midpoint?
It should be close, yeah. Let me label this midpoint Riemann sum. The area using the midpoint Riemann sum is approximately that. And we should get that sum to come out to be 1.003. And again, the midpoint, just so we're clear, is just the difference between the two extremes divided by 2. What do we have down here? So yeah, the right Riemann sum plus the left Riemann sum divided by 2 is not quite the midpoint Riemann sum. So the right plus the left over 2 is 0.994, but the midpoint was 1.003. The exact area, we weren't asked to compute, but just so we have something to compare it to, the exact area of that region under sine from 0 to pi over 2 is 1. So I think what was it? The left Riemann sum was 0.86. The right Riemann sum was 1.1. And the midpoint was 1.003. So the midpoint was closer. But nonetheless, all three were pretty decent approximations only using 6 rectangles. And so that's the basic idea on how we would approximate area under a given function. Do y'all have any questions on any of this? I know it's probably hard to know what questions you have at this point. And this stuff is pretty dry. I mean, it's just numerical computations. But it does, this stuff does lend itself to something very powerful in finding the area under a curve. It doesn't matter what the curve shaped like. There are some exceptions, but we don't look at those. So our detour, before we go back to looking at a more compact definition of the Riemann sum, is the sigma notation. Sigma is, of course, that letter, capital. And so what this is going to do is going to give us a shorthand for writing something plus something plus something plus something. It's going to give us a compact way to write out a lengthy sum, so we don't have to write out, 6 different things or 20 different things. And I guess we'll just look at an example instead of trying to explain the notation piece by piece. But the sigma just means to sum. The thing you have out in front of the sigma is the expression that you're plugging into to sum. So if I said I want to sum k, I have a lower bound or a starting index. So I'll say sum k from k equals 1 to k equals to 5. And so that's your starting value on bottom, the ending value of k on top. And so we start with k equals 1. And then when we change that to k equals 2, we're going to do what the sigma notation means, which is to sum. Then k equals 3, then 4, then 5. If it said sum from k equals 1 to 5 of k squared, then we would just say, well, k is 1, so I have to square that. Then add, so k is 2 squared, and so forth. So that's what we're going to use for shorthand notation. And it can take various forms. It's sum from k equals 1 to 4 of k squared plus 2. For instance, we would have 1 squared plus 2 when k is 1. Then k is 2, so that's plus, or 2 squared plus 2. And k is 3, it's 3 squared plus 2. And then k is 4, so it's 4 squared plus 2. Is everyone clear on that notation, how it works? It's just a compact way to write out a sum. This here.
If you have an additional sum there, though, wouldn't you want to include 0 as well? Like if you have k squared plus 2?
Well, it can start as, we could start it at 0 for 1 and 2.
Because then you'd have a plus 2, and you'd have the entire expression would change, wouldn't it? 'Cause you'd have a 2 in the first
Right.
It'd be a
parentheses.
different interval though.
Yeah.
It'd be k equals 0 to 5. So
Yeah.
1 to 5.
Oh, okay.
Yeah, we would have to start at 0. If we started at 0, then yeah, we have a completely different sum. Each term of the sum looks identical, but if we start at 0, the first term would be when k equals 0, and that would be 0 squared plus 2. And then the next one would be 1 squared plus 2. We're focusing on ones that start at 1 because these k's are going to represent those grid points for us, those x, the x sub k, no, the x star sub k's rather. So we have x star sub 1, 2, 3, 4 all the way to n. Our sums are going to start at k just for that. But yeah, we could start the sum at k equals -12 if we wanted to. So the properties of, summing a bunch of stuff is really just algebraic properties on what you can do when you have a bunch of things added together. One property is that if we have the sum from k equals 1 to wherever, we'll just call that n, of c times an expression involving k, we'll just call that a sub k, or whatever expression involving k is, where c is a real number that constant, the c doesn't, it's like our delta x. So it's just a constant that's in every expression involving k. We could just pull that constant out of the summation and multiply it in afterwards. So like if we had the sum from just a small one here, k equals 1 to 2 on 2 times k, we would have 2 times 1 plus 2 times 2, which is the same thing as just 2 times 1 plus 2. So that's our c. Just like our delta x behaves. And the other property that we're going to use eventually deals with if you have like 2 or more expressions involving k. So like we'll just call that a sub k, and it could be plus or minus another expression involving k. We could sum that up individually. So we could say that's the sum from 1 to n on a sub k plus minus the sum on b sub k. We will utilize those ultimately. So if we had the sum like from 1 to some number of the expression k squared plus k, we can sum those individually. Like that. I should write these down. So those are two properties we're going to use to figure out these sums. There's formulas that we use to compute the other part of it, but this is gonna make our notation specifically for that Riemann sum. It's gonna make it compact.
Does this only work when k equals 1, or does that not really matter?
And it doesn't matter.
Okay.
It doesn't matter what this k is. If we started at -5, it would still, that property would still hold. But again, we're just using k equals 1 because that's for this particular approximation and exact area, that k will be 1. We'll start at 1. So this theorem here is giving us 4 different formulas for summations. And maybe I'll number these. So the first one says that if you sum up from k equals 1 to n of a constant, then that's simply just constant times your stopping point, wherever you stop at. So like, for example, if I had the sum from k equals 1 to 50 on, let's say 10, that means sum up 10. When k equals 1, you get 10, plus k equals 2, 10. So you got 10 plus 10 plus 10, 50 times is how we're interpreting that. So that's just 50 times 10, n times c. The second one deals with just summing up the integers, the counting numbers. So 1 plus 2 plus 3 plus 4 plus 5, et cetera, et cetera. That's the formula for that. Notice all these formulas depend on where we stop. We're all of them start at 1. That would change, but since they all start at 1, these formulas are in terms of where that sum actually stops.
For example, with the ones, would those be equivalent to the k values? So, for example, if your k value wasn't 1, would that 1 then turn to that, from that k value?
For which one are you looking at? All of them, or
Well,
the
all
for?
of it, well, 2 through 4.
Okay.
I guess.
So what?
Well,
Sorry.
because the k value is 1, but in the formula there's also the 1. Is that 1 actually the k value, or is that?
Oh, you mean this one here?
Yeah.
No, it doesn't have anything to do with this, with the starting value.
Okay.
Yeah, and if we start at 0, then these formulas change. So example 2, an example of property 2, or what we're calling number 2. If we had to sum from k equals 1 to 100 of k, that just means 1 plus 2 plus 3 plus 4, etc., all the way to 100. And so instead of like typing that out or trying to compute that, we use the formula. Since we're stopping at this example, we're stopping at 100. That sum, as long as it's the k is the expression here, is just n times n plus 1 all over 2. So somebody figured this out when they were like 14 years old. This was like long ago. But the way they figured that out is they said, all right, well, if I take 100 plus 1, then that's 101. And if I take 99 plus 2, that's 101.
Oh, yeah.
And then you have 50 of those pairs, right? So I have 101, 100 divided by 2, 50 times. 101, but there's 50 pairs of 101. Or 50 occurrences of 101. The k squared rather, that's when we're summing up the counting numbers squared, 1, 2, 3, 4. but they're all squared. And then the other formula is for all of them being cubed. Again, depending on where you stop. You have to make sure that you're summing up the squares when you use this formula and so forth. Those show up when we're actually determining, like, approximate the area using, 50 rectangles, approximate the area using 100 rectangles. These things show up, and instead of actually computing the sum, by adding everything together, we're just going to turn those sums into these expressions involving the stopping point, just to make the computation a lot more quick, efficient. Okay. So are there any questions on summation notation? I would say that for what we have to do in this class, on the exam especially, that you can either remember this formula. There's another formula from another textbook that I've printed out for you that's much, much more efficient, I think, which kind of eliminates the necessity to have to remember these four. But one way or the other, you're going to have to remember something about a summation formula to compute Riemann sums to get an exact area. So all we're doing here is we're redefining the Riemann sum in terms of summation notation, which is right here. So instead of writing out delta x plus f star sub 1 plus delta x times f of x star sub 2 plus dot dot dot, we're just going to write it out compactly using the summation notation. But nothing else has changed. Delta x is the equal length of the rectangles, partitioning A, B. In addition to the, compactifying the notation, what we're getting is a specific way to evaluate or to come up with the thing we plug into the function if we're using left, right, and midpoint Riemann sums. So that way we don't have to find all of the grid points or the partitions. So these three things that we've got highlighted in red, it eliminates the necessity of us to say, okay, well, what's the first grid point? What's the second? What's the third? What's the fifth? What's the 10th? What's the 50th? So with this right here, what we have in red, this actually becomes a whole lot more efficient, especially if you have a whole lot of rectangles. So evaluate the left, right, and midpoint Riemann sum for the function x cubed plus 1 on 0, 2 using 50 subintervals. So 50 rectangles to approximate this area, A to B, on the function x cubed plus 1. So if we're, instead of finding all of the grid points, using what we have up here in red, that's going to change from whichever Riemann sum we're using. So if we're going to take this more efficient approach, the only thing that kind of remains consistent through the left, the right, and the midpoint Riemann sum is this delta x. So that delta x will be the same for all three. The function will be the same for all three, but that's it. We're not going to waste time finding 50 subintervals. So the right Riemann sum, and let's just say first, since delta x is present in all of those, we'll just find delta x, the length of each rectangle. So delta x is 2 minus 0 over the number of rectangles. So 2 minus 0 over 50, which is 1 over 25. So that's the length of each rectangle, whether we're using left, right, or midpoint Riemann sums. So our right Riemann sum. Remember these, what we have here in red, those x stars, that's the expression that has to get plugged into your function. So what we're looking to do is fill in the gaps for this formula here from k equals 1 to n, and our n is 50. Of f evaluated at x star sub k times our delta x. That's what we have to fill in. The x star sub k is different for each Riemann sum. The function is still the same. It's always going to be x cubed plus 1 for this example. So the next thing we need to do is we need to find x star sub k for the right Riemann sum and plug that in. The function x cubed plus 1, because we need f of x star to go into that summation. Okay, so we have x star sub k for the right Riemann sum. We'll go up here. For the right Riemann sum, x star sub k is a plus k times delta x for k equals 1 to 50. So for us, our a is 0. K is just k, and delta x is 1 over 25. So it's 0 plus k times 1 over 25. Or just k over 25. And notice we don't have to worry about the first one, the second one, the third one, the fourth one, because when we plug that into this sum right here, that's going to account for the first one, the second one, the third one, the fourth one, the fifth one, the 50th one. So we just have this x star sub k. Whenever you compute it, it's going to be a function of k, and then you're going to plug that into the actual function f of x, so that f of x becomes f of k. So you'll have this thing right here turning into a function of k. That's in front of the summation that operates on k. So then we have a function of k ultimately in front of the sum that operates on k.
What did we say k was equal to? Like just in general, what is k?
It depends on what you're using it for. Here we're using it for those x stars, which is the first point in the first subinterval to tell us the height, the next point and the second subinterval to tell us the height of that rectangle, and so forth. That's what our k is here.
Okay.
Yeah.
So in this case, with these equations, like in our previous ones, we were using k essentially as our number of subintervals, right?
No, k was associated
Or was
with
that the domain?
Well, it was associated with those x sub k's, and with those k went from 0 to n, but with the x stars, k ranges from 1 to n.
Oh,
So,
okay.
these, remember, these were giving us our grid points. Those are like the end points of each rectangle. But we to be more efficient, we're not going to list all of those out anymore.